We are familiar with the idea that things can be positively or negatively charged, and that like charges repel each other and opposites attract. Here we want to be more specific. If we had an object which had a certain charge, how strongly would another charged object be pulled or pushed, and in what direction exactly? First, we consider a point particle with a positive charge Q1. We know that if we were to put another positive charge, Q2, anywhere in the space around the first particle, it would be repelled. How strong would the force be? I can tell you that the size of the force will depend on three things: the size of the charge Q1, the size of the charge Q2, and the distance between the charges, r. This force will act on both particles in opposite directions to each other. To be exact, the force is equal to Q1 times Q2 all over r squared. When we use SI units, we need to include a constant in the equation. We usually write this constant as 1 over 4 pi epsilon naught. Pi is familiar, and epsilon naught is called the permittivity of free space. The form of this constant is not important, we just choose to write it like this. The only purpose of the constant is to make the equation correct in the SI units of newtons, coulombs, and meters. Let's now swap this arbitrary charge for a positive charge of 1 coulomb, which we will call a positive unit charge. This idea of a positive unit charge will be used a lot. We know that if placed at any point in the surrounding space, this unit charge will feel a force, which using this equation, we know will have magnitude equal to 1 over 4 pi epsilon naught Q1 times 1 over r squared. And it will be in the direction away from the central charge. Since we know the size and the direction of the force, we can draw this force as a vector like this. We move around this unit charge, and at every place we put it, we draw the vector of the force it feels from the other charge. The complete set of all of these vectors, drawn at every point in space around this central charge, represents what we call the electric field, due to the central positive charge. The electric field around a charged object describes the size and the direction of the force that a unit positive charge would feel from it, at every point in space. We usually call the electric field E, and the equation looks like this. E is equal to 1 over 4 pi epsilon naught, Q1 over r squared, with an r hat unit vector. The underlines indicate vectors, and the r hat unit vector shows us the electric field points in the same direction as from the particle to each point. Since we can't physically draw an arrow at every point in space, when we want to draw an electric field, instead of drawing electric field vectors, we instead draw field lines, which are continuous lines that point in the direction that a positive charge would move, so the same direction as the vectors. To indicate the strength of the field when we draw field lines, we draw the lines more densely when it is strong and more spread out when it is weak. For example, this region has a field about 4 times stronger than this region, since the lines are about 4 times more densely packed. Notice that the only times that field lines are created or disappear are on charges. If we instead want to work out what the force would be on an arbitrary point charge, Q2, all we have to do is multiply the electric field vector by the charge Q2. This will make the force vectors multiply in size by a factor Q2. Notice that if Q2 was negative, the force vector would now be in the negative r hat direction. In other words, the particles will attract rather than repel. I have described the forces between 2 point particles and the electric field created around a charged particle very generally, and I summarise them here. The force between 2 particles with charges Q1 and Q2 is this, and the electric field around a particle with a charge Q1 is this. Both are vectors which have a size and a direction, and to get from one to the other we just multiply or divide by Q2. Here we have 3 questions. The first asks us to evaluate the force felt between 2 charges for 3 different situations. This is just a case of plugging in the numbers to the force equation. For 1, we plug in 3 and 0.5 to get this. For 2, similarly, we get a result of this. And clearly, in part 3, if the charge is 0, there will be 0 electric force between them. For question 2, we are asked to write the expression for the electric field around a negative charge and to draw the field lines. Here we again must remember to include the r hat and the negative. This now says the force points in the negative r hat direction, which will be towards the charge. This means that a positive unit charge will be attracted to a negative charge, which is what we expect. Now we just need to draw the field lines, indicating that it is stronger closest to the charge than further away. The last question tells us that a test charge of negative 0.2 coulombs is placed near a 0.1 coulomb charge and feels an attractive force of 28.8 times 10 to the power of 6 newtons and asks us to find out the distance between the two. We identify that the force equation applies in this situation, and we rearrange it so we get the distance in terms of everything else. Then we just sub in the numbers and we calculate the distance to be 2.5 meters.